Hey, welcome back, everyone. This is part 2 of your practice final exam for statistics. Part 1 was 1 through 16. Part 2 is going to be problems 17 through 34. And let me pull it up. Again, you can find this as a PDF in Canvas. And I'm presuming that you have a copy of it either printed out or in front of you so that you can follow along. And again, I'm assuming that you can see the questions. So for number 17, we're looking for the mean of a probability distribution. And the mean is going to be 3 times 0.14 plus 6 times 0.29 plus 9 times 0.36 plus 12 times 0.11 plus 15 times 0.1. And this is probably the X bar. All right. So I'm going to type it in just the way it looks. So 3 times 0.14 plus 6 times 0.29. Oops, plus 9 times 0.36 plus 12 times 0.11 plus 15 times 0.1. It's going to give me a total of 8.22. And what that means is you can see with the distribution that the big heavy probabilities are the 6 and the 9s. That's the 0.29 and the 0.36. Those are the bulk of it. And so you can see a little over 8 being the mean, the middle of that distribution. Number 18. 18, we could do it by hand, but I'm going to show you a faster way to do it. So what I did was I went ahead and put in for list 1, the 0, 1, 2, and 3. So here's my list 1, 0, 1, 2, and 3. And then I put the probabilities in list 2 in that order, the 0.46, 0.41, and so on. And then I'm going to do this now. I'm going to go ahead and run one var stats, because we're looking for the standard deviation here. So I'm going to do stat one var stats under calculate. And the list, I have, my first list is in list 1. So second 1 be list 1. My frequency list is second 2. So now I'm using 2 lists. Before we didn't have a frequency list. We're going to calculate. And you can see my standard deviation is right there. So nice and easy. You could do it by hand. There is a formula to do it, but you know, why if we don't have to? Number 19. So now we're to expected value. So suppose you buy one ticket for $1 out of a lottery of 1,000 tickets where the prize for the winning ticket is to be $500. What is your expected value? So I'm going to set up a table. So win, lose. And here we're going to have our X, and then our P of X. And then our X times P of X. And down below, we're going to have our summation. All right, so if you win, you only get $499 because, let's use a different color, because you've already paid $1 to get into this. So you win $499. However, your probability of winning is only 1 out of 1,000. That's a good. So when I multiply the two, I get 499 over 1,000. If you lose, you're out $1. And your probability of losing is quite high. You have 999 chances out of 1,000 of losing. When I multiply the two together, I get negative 999 over 1,000. Now you'll note when I add up my probabilities, I get 1. That should always happen. When I add these up to get my expected value, 499 minus 999, so 499 minus 999 is 500, negative 500. And that translates into a negative 50 cents. And that is your expected value. If you play this particular lottery over and over and over and over again, most of the time you'll lose, occasionally you'll win. Overall, you're probably gonna be down. Now, number 20, let's flip the page. So number 20, a test consists of 10 true, false questions. This is 20. Ten true, false questions, that's my N. To pass the test, a student must answer at least 6 questions. At least, and by the way, because it's true, false, the probability of winning each time is 0.5. And X, this is, by the way, a binomial distribution. X is bigger than or equal to 6. If a student guesses on each question, what is the probability the student will pass the test? Okay, now if you remember in class, greater than, we can't do directly in our calculator. So let me show you what we're going to do. So it's possible the student takes the test, answers all 10 questions and gets none of them correct, or gets 1 correct, or gets 2 correct, all the way up to all 10 correct. Now, we want to know what they are looking for. What they want is 6 and bigger, because it says at least 6 questions. But our calculator can only do below. So here's what I'm going to do in my calculator. To compensate, I'm going to do 1 minus binom CDF 10, 0.5, comma, and what's the opposite of 6 and up? That's going to be 5 and down. Let me show you how that looks in the calculator. So I'm going to go to my distributions, second distribution. I'm going to go down to binom CDF. And number of trials is 10. P is 0.5. And the X is going to be 5 and down. I'm realizing I just forgot 1 minus. So let's clear that. So 1 minus, second distribution, binom CDF, we want the cumulative, 10.5 and 5, paste. And so it's going to be 1 minus that is going to give me my probability. And they say run to 3 places, that's fine, 0.377. Make sure you practice these with your calculator before the final, right? Make sure you're real comfortable with that. By the way, we know it's a binomial distribution because we have a success or a not success, a fail. Those are the only 2 choices. By means 2, right? So number 21. In a certain college, 33% of physics majors belong to ethnic minorities. If 10 students are selected at random from the physics majors, what is the probability that no more than 6 belong to an ethnic minority? So once again, P is going to be 0.33. N is 10 again. X, no more than 6. So this means less than or equal to 6. So number to the less than. So this is just going to be regular binom. CDF, 10.33. And just regular 6 and down. And there's not a 1 minus in this case, because in this case, they already want the less than. Here it's 10 again, 0.33 and 6. And this one also is rounded to 3 decimal places, so 981. Number 22, a tennis player makes a successful first serve 51% of the time. That's our P. If she serves 9 times, there's my N. What is the probability that she will get exactly 3 serves in? X equals 3. Now, the first 2 were inequalities, so we used CDF. If it's exactly equals, we're going to use PDF. PDF. Trials is 9, P is 0.51, and the X value is 3. And this does not say where to round it. We'll go to 3 again. Number 23, are we doing with the camera? We're good. A multiple choice test has 12 questions, of which has 5 possible answers, only one of which is correct. If Judy, who forgot to study for the test, guesses on all questions, what is the probability that she will answer exactly 3 questions correctly? So in this case, N is 12. P, because there's 5 possible answers and only one of them is correct, that's a 1 in 5 or a 0.2 for P. And in this case, X is exactly going to equal 3. So we're going to use binom PDF again. And you could put in 1/5 or 0.2, it doesn't matter. In fact, I'll show you in the calculator when I do the 1/5. Binom PDF. Trials are 12. Watch, I can do 1 divided by 5 directly into P there. And the X value happens to be 3 again. Rounded to 3 decimal places again, just because that's what they seem to be wanting. All right, next up, number 24. Let's scooch this up a little. So according to a college survey, 22% of all students work full-time. Find the mean for the number of students who work full-time in samples of size 16. So in this case, N is 16, P is 0.22. Now the mean is N times P. .52. So this is 3.52. And what that means is in any given group of 16, there'll be between 3 and 4 that are working full time. in that group of 16. That's how we would interpret that. 25 is the same information, except now they want the standard deviation. And standard deviation is n times p times q. Remember, q is 1 minus p. So in this case, we have n is 16 again. P is 0.22. And q, 1 minus 0.22. So plugging that in. Now, if you forgot this formula, it is here and here on this sheet. All right, so we have square root 16 times 0.22 times 0.78. Now be careful. Again, your calculator may be different than mine. It may not have the radical bar like that going all the way across. So you may need to put in some extra parentheses depending on your calculator type. So this is about 1.657. All right, so next up, 36. Or 26, pardon me. And here we're looking for z sub 0.36. Now, the 0.36 is always the area to the right. So this area here is 0.36. Now, if you remember when we use inverse norm, under distributions, it needs area to the left. So when I run it, when I ask for area, I have to do my 1 minus trick. And this is standard normal. So the mean is 0, standard deviation is 1. We get this. Now, again, if you have an older calculator, it will just say inverse norm, and you'll type it in just like that. The commas are right here, below the sign button, above the 7. And so this gave us 0.358. 26, 27. And to be clear, that's this mark right here. By the way, if you round this number off to 2 decimal places, it's 0.36, and that also happens to be 0.36. It just is a pure coincidence that those happen to be the same number. Don't look into that whatever's there is always the area. That's not true. All right, so 27. Assume that adults have IQ scores that are normally distributed with a mean of 100, standard deviation of 15. Find the probability that a randomly selected adult has an IQ between 90 and 120. So I'll go here. So we are looking for that area, and we're going to be using normal CDF, and it's from left to right, 90 to 120, then the mean, then the standard deviation. Second distribution, normal CDF, oh, too far. The lower is 90. The upper is 120. The mean is now 100. Standard deviation is now 15. 0.6563. Number 28. Let's get a new piece of paper. Number 28. The diameters of bolts produced by a certain machine are normally distributed with a mean of 0.3 inches and a standard deviation of 0.01 inches. Find what percentage of bolts will have a diameter greater than 0.32 inches. Let's draw this out. That's the mean there. They want to know bigger than 32 inches, or 0.32 inch, I should say. And this is 0.32. So in our calculator, we're going to put normal CDF. Left boundary, or the lower boundary, is 0.32. The upper is just any big number. I just put a bunch of 9s. The mean is 0.3. Standard deviation is 0.01. This is normal CDF. The lower bound in this case is 0.32. The upper bound is just some big number. The mean is 0.3. Standard deviation 0.01. Not too bad. Number 29. Scores on a certain test are normally distributed with a mean score of 60 and a standard deviation of 5. What is the probability that a sample, that changes things, of 90 students will have a mean score of at least 60.527? Now we have a sample involved. So that's going to change our standard deviation. Now our mean is still going to be our mean. That's going to be the same, which is 60 in this case. However, our standard deviation is now going to be our original standard deviation over the square root of n. The original standard deviation was 5 divided by the square root of 90. Now, it's going to also make the graph spike a bit more. So the mean is still 60. And they want to know at least 60.527. That's pretty close to. So 60.527. I'm going to exaggerate that a little bit. And this is 60.527. That looks like it's going to be close to, well, I don't know. I don't want to make any predictions. Let's actually do it. So now I'm going to go to second distribution, normal CD. F, the lower bound is now 60.527. The upper is 9999 again. The mean is 60. Now the standard deviation is changing, but I can actually type it in just like that. 5 divided by the square root of 90. It'll make that computation for me within it. Here we go. Let me write down what I typed in. I got that. And let's scooch this up a little bit. All right. The weights of number 30. The weights of fish in a certain lake are normally distributed with a mean of 20 pounds and standard deviation of 9 pounds. If 9 fish are randomly selected, what is the probability that the mean weight will be between 17.6 and 23.6? Okay, so once again, we have a sample of 9 fish. So this means that my mean stays my mean, which is 20. Standard deviation, however, because of the central limit theorem, changes to 9 divided by the square root of 9. And they want to go from 17.6 to 23.6. Now that looks a lot more symmetric than I think that it actually is, but that's okay. Normal CDF, 17.6, 23.6, mean of 20, and standard deviation of 9 divided by root 9. Now, we know root 9 is 3, and then 9 divided by 3 is 3, but I'm going to keep it all in there in case you run into one that it doesn't come out nice and pretty like that. All right. Normal CDF, lower is 17.6, upper is 23.6. The mean is 20. Standard deviation is going to be 9 divided by the square root of 9. And this one's not hard. You could actually calculate that one. And let's paste it. Uh, 6731. That's number 30. So you only do that divide by the radical when you have a sample. All right, number 31. Oh, I'm not going to read all that. Basically, the mean is 0 degree, excuse me, 0 degrees Celsius, and standard deviation is 1. And for 31, what we're going to have is they want the 40th percentile. That's the bottom 40%. Bottom 40%. Now, when they give us the area of the probability, that means we're going to be using inverse norm. And inverse norm, again, is always area to the left, which we already have. So we don't have to do a 1 minus in this case, 0.4. Now, this is a temperature in degrees Celsius. So this is negative 0.25. I'll just put there. The 3 doesn't fit. So this horizontal axis is the temperature in degrees Celsius. $32. We don't have to go that high. Let's go to there. 32. A sociologist, so we're looking for a confidence interval for the population mean, mu, and we're assuming that it's a normal distribution. A sociologist develops a test to measure attitudes towards public transportation. And 27 randomly selected subjects are given the test. Their mean score is 76.2 and their standard deviation is 21.4. Construct a 95% confidence interval for the mean score of all such subjects. All right, so this is going to be a t interval. And very nicely, the calculator does all the work for us. So we're going to go to stat and tests. And we're going to go down to a t interval. By the way, it's t and not z because we don't know anything about the population standard deviation. We only know the standard deviation of the sample. I lost it. There we go. So a t interval. And we don't have raw data. We have to use stats. X bar, they give us 76.2. Standard deviation of the sample, 21.4. N is 27 people. And the confidence level is 0.95. And then it just does everything for us. It's wonderful. And let me write some of this out. So X bar was 76.2. Sample standard deviation was 21.4. And N is 27. And the C level is, in this case, 0.95. And we got the confidence interval is 67.734 and 84.666. So there is my confidence interval. Almost there, only a couple more to go. 33. So in this case, we're looking for a minimum sample size of an unknown population mean mu. Now, for this one, we're using this formula here. We don't have a snappy way of doing this. We're using this formula here. And the sample standard, the population standard deviation has to be known to be able to use this formula. So let me write down the formula. N equals Z sub alpha over 2 times sample standard deviation, or population standard deviation over the error. And let's figure out each of these based on the information. So how many students must be randomly selected to estimate the mean weekly earnings of students at one college? We want a 95% confidence, so our C level is 0.95. Now that means alpha is 0.05, and alpha over 2 is half of that, which is 0.025. And we know Z sub 0.025. We can figure that out right here. Remember, that's area to the right, so I have to do the 1 minus trick. Inverse norm, 1 minus 0.025. That's about 1.96. All right, we are also given 95% confidence interval. That sample mean is within 2, so that's our error, E, is $2 of the population mean, and the population standard deviation is known to be 10. Let's put everything together. Oh, I forgot to square the whole thing, is the formula. Yeah. 1.96 times 10 over 2 squared. So I'm just going to use all that number. Why not? Times 10 equals divided by 2 equals, and then square the whole thing. So this gives us about 96.036. Now, remember, no matter what, we always round up. We want to make sure we have at least the number of people that we need. So this rounds up to 97 students. And last problem for this video. So use the given degree of confidence sample data for a confidence interval for the population standard deviation. This one's going to be more work. In fact, I'm going to get more space. All right, 34. So this one's going to take a minute or two to do. First of all, we have that n is 20. And the mean we don't need for this, what we're doing, but I'll put it down anyway. Mean is 9.4. Standard deviation, this is the sample standard deviation, is 2.5. All right, so our sea level is 0.99, which means alpha is 0.01, which means alpha over 2 is 0.005. So this is a chi-squared distribution. And we will need these critical values. And within each of these, the area is 0.005, 2 zeros. And in the middle is our 0.99. All right, so with the chi-squared, we need degrees of freedom. And so based on n, our degrees of freedom are going to be 19. And we need this table to find these values. Let's see if I can squeeze. We need 19. No, I don't have to cover it up. So degree of freedom is 19. Now, to be clear, area to the right, if you notice, this table is area to the right now. So the z and the t are area to the left when we're using the calculator. This is area to the right. So the area to the right of the left one is 0.99 plus 0.005. So 0.99 plus 0.005. So 0.995. 0.995. I'm going to go down to degrees of freedom of 19. There we are. There's my left one. 6.844. 6.844. 6.844. Now, area to the right on this one is just a 0.005. So I go to 19, 0.005, and I go down to where they meet. And that is 38.582. 38 point, oh, I lost already. What was it? 19, 582. Why do we need those? Because the formula is here, except this is variant. So we actually have to take the square root of both sides. And you can see there's chi-squared sub r, chi-squared sub l. Let me write the formulas here for you. All right. So here's the formula. N minus 1 sample standard deviation squared over chi-squared r And then the same, except the other denominator. All right, so we're going to put everything. Now, I'm not going to write 20 minus 1. I know that that's just 19, so I'm just going to put that in there. Now, on the left side, we're using the right one. It's kind of looks opposite. And then it's this one here. And now we're going to get our decimal approximation. Now, again, I can use my radicals for all of it. You may need to compartmentalize them with parentheses. So 19 times 2.5 squared divided by 38.582. $1.754, we'll say. And then we have radical. 19 times 2.5 squared divided by 6.844. We get 4.165. There's our confidence interval. And no, there isn't a magical program in here that will do that for you. It's not there. So you have to kind of go through all these steps, even archaically go through this table. So that was problems 17 through 34. Problems 35 through 44 will be in the next video. I hope this was helpful. Take care.